that. All right, so last one on virtual machines. So we'll go through this and then we can answer questions about the lab or final or talk about that and do that stuff. So virtual machine, it's won't be on the file, but it's a good thing to know because you will encounter it in your life, and knowing all this stuff, we're not actually going to probably learn that much new. It's going to actually be kind of review because everything we've learned actually applies to virtual machines. The only difference is a virtual machine abstracts the entire machine. So like how a process thinks it has access to all of the memory with virtual memory, while a virtual machine thinks it has access to the entire machine when it may not. So you can run multiple operating systems all on the same machine. They each believe they have access to the full machine, but none are aware of each other, and they're all actually sharing it. So there's some terminology with virtual machines. The first term you'll hear is the host. So the host is the thing that has direct control over the hardware. So if you're actually implementing virtual machines, there's something that manages all the virtual machines, and that is called a hypervisor or a virtual machine manager. You'll probably see it more oftenly referred to as a hypervisor. So that controls virtual machines, controls creating them, managing them, what resources it gets, so what hardware it's actually able to access. So some virtual machines might access different subsets of hardware, or you might make up your own hardware to give the virtual machine, and the virtual machine's just not going to know any better. So when you actually implement hypervisors, there are two types, and why you might care about them is one, well, it's kind of interesting, and two, one is a lot slower than the other one. So type 1 is a bare metal hypervisor, so it runs directly on the hardware, and this requires special hardware support, as we'll see. And the other is a type 2 hypervisor, so that's called a hosted hypervisor, which simulates a hypervisor, but it just runs as a normal application. So you are running a kernel in user mode. So there are some tricks you need to do if you need to actually accomplish that task. Typically, the type 2 hypervisors are going to be slower because it doesn't require any special hardware. It's just running as a process, and we're going to do some tricks so it can actually run as a normal process, even though we know the kernel actually runs in kernel mode. And then the other term is a guest. A guest is just the operating system you are running with that hypervisor. And each guest sees its own copy of the host, thinking it has access to the whole machine when it may not. So this is our kind of lay of the land. So far, we've been used to the picture on the left, so figure A there, where we have a bunch of processes. It talks to the kernel through a programming interface, which we know for Linux at least are system calls, and then the kernel goes ahead and interacts directly with the hardware. Now, when we have virtual machines, we still have that same system call interface. Nothing changes. The processes and the kernel are all the same, but now the kernels are running under a virtual machine, and then they're all managed by this virtual machine manager or hypervisor, which then has direct control over the hardware. So we have another layer of indirection here. So as a note, you might hear the term emulation. So virtual machines are typically not emulation, but they can do it. So emulation is typically when you translate one ISA or instruction set architecture to another. So your phone runs on ARM, and your laptop, as long as you don't have a Mac, is x86. So if you want to run, say you want to run an iOS application and actually run it on your computer, well, you're going to have to emulate it. You're going to have to change ARM instructions to x86. But typically, when we care about virtual machines, whether or not we emulate it doesn't really matter to us, and we'll just assume that we're not emulating at this point. So if you do have to emulate, it's going to slow down because for every instruction you have to actually translate it, which is going to slow it down. So this is okay for some uses. So if you're interested for a little fun project, you can emulate a original Nintendo system quite easily, and you can emulate it because your hardware is like 2 billion times faster than the original Nintendo, which is like an 8-bit CPU running at like half a megahertz. So with some things, you can go ahead and emulate it. With other things, you might have to do some more advanced techniques that we won't get into in this course. So If your virtual machine does have to emulate an instruction set too, the performance is going to be worse, so we'll just talk about things that are actually the same underlying instructions for the same CPU. So some fun things about virtual machines is they enable pause and play. Exactly like changing processes, you can change virtual machines. So a hypervisor can go ahead, pause an operating system, switch to another one to execute, go back and forth between them at will, even move them between different hosts if you want. It's not a problem for virtual machines. So your hypervisor is going to need the context between virtual machines, and it works the exact same way as context switching between processes. So the only difference here is our processes are actually going to represent the entire CPU, including all like special kernel mode registers and everything. But aside from saving some more data, it's fundamentally the same thing as switching between processes. So it's all stuff we already know about. They also provide some protection through isolation. So guests, like processes by default, are all isolated from each other and the host that's actually running the operating system. So if you're the hypervisor, you can go ahead, you can set limits on like how much CPU time each guest can take, how much memory they can take, maybe how much network bandwidth they can have. And that way, if one of the machines gets hacked or something like that, well, it only has access to its own virtualized hardware, so it's probably fine. You can even disable it if you want without affecting everything else. Like for example, if you download, anyone know what Red Star Linux is? No one's heard of that? So that is the official operating system of North Korea. So you can, if you want to try that out, typically you wouldn't want to install it on your actual hardware because you have no idea what it will do. But if you're interested in it, hey, you can install it in a virtual machine, and probably a good idea not to give it network access. And then you can just kind of see what it does, and it's fine because it doesn't have access to anything. So that's some fun thing you can do. Yep.
Why is it not a good idea to give it network access?
Because it's from North Korea.
Wait, what?
Yeah.
Wait, what's from North Korea?
Red Star Linux, it's called. So it's.
Wait, why are we still using it from North Korea?
Hopefully you're not. If you're using it, that's probably bad. So yeah, so if a virtual machine, becomes infected with a virus or gets compromised with someone hacking into it, or it's pre-compromised by North Korea, well, you can just go ahead and remove it when you're done with it. So other things it helps with are if you've ever used cloud services, you've all used virtual machines because that's all they run. So in data centers with lots and lots and lots of machines, well, often they don't make use of all the resources, and being able to actually move virtual machines around is actually great for helping balancing the load. So like with processes, they're kind of, instead of being tied to a CPU, they're tied to an actual machine. So we could have the case where, hey, we assigned a bunch of virtual machines to a server, and now everyone's using all those virtual machines. So all the they're pegging 100% of the CPU, and now the physical machine doesn't have enough capacity to serve them all. So what you can do is you can transparently just move a virtual machine to a host that doesn't have any load while the user's still running it, and they won't notice, and suddenly everything will be much faster from them because they just got moved. So cloud services will do that all the time, and they only care about running virtual machines for you. So, and also because they're virtual, well, it also helps you with your architecture. If you're building like a big web server or something like that, well, you could put your database on a virtual machine, you could put your web server on a virtual machine, and then when you're small with like only a few users, well, you can run all the same virtual machines on the same physical machine since there's not that many people using them. And then as you get more users, well, you can just buy another machine, and instead of running both virtual machines on the same computer, each computer can run its own virtual machine where that's the only thing running. So you don't have to change anything, you just reconfigure what virtual machine runs where, and then you're done. Yeah?
What's the difference between a virtual machine and a container?
We'll see that at the end. So the question is, what's the difference between a virtual machine and a container? So we'll get to that at the very end. So for this, the key abstraction is a virtual CPU that represents the entire state of the CPU, including all of the specific kernel mode registers and other stuff you wouldn't be able to see in user mode. So for processes, it's like part of the process control block. It kind of acted as a virtual CPU, but only had access to user mode registers. There's special kernel mode only stuff that we haven't really gone into. All you need to really know is that there are special kernel only mode registers and things like that that you can only do in kernel mode. For example, changing the page table or something like that. So the vCPU structure just holds the entire state of the CPU. And when the guest isn't running, it gets context switched in like normal for processes. So it would just save all the additional registers. And when the guest isn't running, it just saves that. And when the guest gets context switched back in again, it just reloads it all again, and it's all good. So this may seem kind of weird, especially given what I said about type 2 hypervisors and the fact that the kernel is running and it's completely unmodified. So you are running a user mode, you just have like a normal user process, and you're running the Linux kernel that is unmodified, so it's going to execute instructions that are only available in kernel mode. So how does that work? So remember on x86, everything in user mode is running in ring 3, which were the names of the modes, and then kernel mode was ring 0. So you are essentially running your guest in mode 3 only, and it's going to make use of instructions that happen in mode 0 because it thinks it's the kernel. So if you're doing a type 2 hypervisor, you have to do some tricks. If you're doing a type 1 hypervisor, this is supported for you. So if you have hardware support for a hypervisor on x86, you can tell how old this is because if they designed this when virtual machines were actually a thing, they would probably have called it ring 0. But now, since they ran out of numbers, hypervisor is ring -1. So that's where that number comes from, because when they first designed the instruction set, well, hypervisors did not exist. So that's for hardware support, there's additional mode. And then for type 2 hypervisors, everything runs in user mode. So if you're implementing a type 2 hypervisor, one strategy you can do is something called trap and emulate. So if you just naively just run kernel code as a user process, well, you're going to get a signal, which is going to generate a trap in the kernel whenever you try and execute that instruction that is only supposed to be run in kernel mode. So you'll get a signal that says, hey, you have an illegal instruction. So if you are actually implementing the hypervisor, you'd have to know some details about the hardware. So you can handle that illegal instruction call, and you can simulate what actually goes on, what's actually supposed to happen with that instruction, and update the virtual CPU. So you'd have your own structure for a virtual CPU where you have to actually know about the hardware and keep track of stuff. So then you just simulate that instruction. And what this is going to do is one cause for slowdowns, because every time I'm executing instruction that I'm not allowed to execute, it's going to generate, it's going to have to be handled by the actual host kernel. It's going to generate an illegal instruction to your process, and then you're going to have to do something to simulate that single instruction. So there's a lot of steps whenever you encounter a kernel mode only instruction. So this is what it kind of looks like visually. So at the top of the big line is the guest, and then at the bottom is the hypervisor or whatever is running it. So in this case for type 1, the whole thing's a user process. So if your guest kernel makes a privileged instruction, which is an instruction running in kernel mode, well, it's going to generate the trap, and then instead of just failing, then you're supposed to handle that and simulate it, and then you update the virtual CPU, and then you just keep executing the next instruction and keep going on. So that's nice if you have a very well-designed instruction set, but this doesn't always work, especially for x86. So if you have this clear boundary, all you have to do is trap and emulate, and you can actually implement a type 2 hypervisor. But x86 didn't know about virtual machines and the importance of this nice clear boundary when it was designed. So it has this nice property, if you can call it that, of instructions, the same instruction behaving exact or completely differently based off what CPU mode the CPU is currently in. So one example is the popf instruction. So what it's supposed to do is load a flags register from the stack, and this behaves differently whether it's in kernel or user mode. So if you are in kernel mode and you execute this instruction, it updates kernel-specific flags. And if you're in user mode and execute this instruction, it updates user mode-specific flags. So it does two completely different things depending on what CPU mode you are in. And this is a problem for our type 2 hypervisor because everything's running in user mode. So if your kernel actually expects the kernel mode version of the instruction and you just blindly execute it, well, then you're going to execute the wrong thing, and probably there's going to be some very hard to debug thing going on. So you can't generate a trap in this because it's still a perfectly legal instruction. It just behaves completely differently. So these are called special instructions and need another approach. So they need something called binary translation. So what happens is if the guest virtual CPU is in user mode, we don't have this problem because the guest expects to be in user mode, and we are currently in user mode, so we can just execute the instructions. You only have to do something if the guest thinks it is actually in kernel mode. So if the guest is actually in kernel mode, you have to inspect every instruction before you execute it and see if it's a special instruction. And then if it's a special instruction, then you do the same emulation or simulation of it, and then skip that instruction and go to the next one. So this is going to be a slowdown, and another thing, you can tell when when the guest expects to be in kernel mode, because there's going to be an instruction that switches from user mode to kernel mode, and that would generate a normal trap instruction, or a normal trap, which would be an illegal instruction. And as part of the simulation, you would update that, hey, my virtual CPU should be in kernel mode. So since it's in kernel mode now, I also have to start analyzing and doing this binary translation just in case I run into a special instruction. So your performance is going to be worse because now when you are in kernel mode, if you are running this type of architecture, you have to start inspecting every single instruction, which is going to be much, much slower. And this is what it looks like visually. It's kind of the same thing, but instead of just relying on a trap to get generated, when you try to execute an instruction, this will look at the instruction, see if it's one of these special instructions, and then simulate it by updating the virtual CPU and then just returning and continuing execution as normal. So this is where the type 1 hypervisors come in. So there's more hardware to the rescue. So they were introduced in 2005. Intel introduced virtualization, calling it VTX, and AMD did in 2006. It was called AMD VE. And if you start playing with virtual machines, you might have to go into your BIOS and enable some settings to actually enable this hardware support. And annoyingly, it's called different things. So Intel codenamed it Vanderpool was in development and published it as Virtual Machine Extensions, VMX. So if you have an Intel motherboard and you try and enable this, it might be under one of three names, and it might change depending on what motherboard manufacturer you're going to. So on some, it might be called Vanderpool. On some, it might be called VTX. On some, it might be called VMX, but they're all the same thing. It's just that hypervisor support. Then AMD, same thing. They called it Pacifica and then published as Secure Virtual Machine. So again, there's three different names it might be called if you have an AMD motherboard. But all it does is add the concept of -1 or hypervisor mode. So what happens if you enable this? Whenever you boot your operating system of choice, well, it's going to claim the hypervisor and also act as a hypervisor. So if you boot into Windows, it will know that, hey, this mode's enabled. I can grab it and actually be a hypervisor. And that way, if anyone runs a virtual machine, I can provide hardware support for it, so it'll be nice and fast. And same with Linux. Linux can do the exact same thing. So that way it can set isolation for the guests and what hardware it wants to virtualize. So now that we have virtual machines too and multiple virtual machines, we have to schedule them. Luckily for us, this scheduling is exactly the same as we saw before. So we can do some things. So maybe you care more about with virtual machines like that processor affinity. Maybe you want to keep something on a single core just so you have closer to realistic performance. So if you only have like one CPU on the physical machine, you could still have a host with multiple CPUs. You would just have to context switch between them. And yeah, so now we're the hypervisor, we have to map virtual CPUs to actual physical CPUs and then schedule them like processes. But this isn't anything new. We can round robin them. We can do completely fair scheduling, or we can try and just like, if we have way more physical cores than there are VCPUs, we can just assign them directly to them and not move them around. So yeah, like I said, if we have more physical cores than all virtual CPUs, we just map them one-to-one and don't even bother context switching. If you have to share, things get a bit more complicated. But if you have like equal numbers of vCPUs and actual physical CPUs, you can still map them one-to-one because the hypervisor threads won't actually run that often. If everything's just assigned to one core, the hypervisor just does some housekeeping and might be called if you're accessing some hardware, but other than that, it stays pretty quiet. So this has some additional problems where, well, now the guest operating system might now run too unpredictably for soft real-time tasks. So if you're running something on actual hardware where you're relying on your round robin to be every 10 microseconds and be it very, very consistent, well, if you are running it on a virtual machine, something that previously met all of your deadlines might no longer meet all your deadlines, because between your round robin ticks, you could be context switched out and then later get context switched back in. So the virtual machine might only think 10 milliseconds has actually passed, but it will be longer than 10 milliseconds, and then you'd probably miss your deadlines. So you might actually see some effective virtualization if you really, really care about soft real-time systems, because there's going to be some additional overhead. And now, also, virtualized memory management gets a lot more complex. So all the kernels are going to still have all their page tables, but now the kernels usually just maps a virtual address to a physical address. But now, since it's a virtual machine, that physical address is actually a virtual address. So the hypervisor has to map what the virtual machine thinks is a physical address to a real physical address. So it thinks it's managing the entire address space, but it is not. So we have to virtualize that too. And this problem gets even worse if we are overcommitted on memory. So that means all the virtual machines take up more memory than we physically have, and in which case your hypervisor is going to have to implement page replacement and do all the paging for you, which gets much more complicated if you dive into the details. So this would make use of something called nested page tables. So again, the guest thinks it has control of physical memory and does all of its normal page table management, but now the hypervisor needs to actually do that. So if you have hardware support, it will maintain a nested page table that retranslates for the guests. So you only have an additional hop to translate all the addresses. And because you have hardware support, you can actually, in your TLB, you could go ahead and cache the whole virtual address from the virtual machine to a real physical address. So on cache hits, it's still fast, so you get all your performance back, but you need kind of hardware support for this. And then if you're overcommitted on memory, it gets really complicated. So you might have double paging. So your kernel, unmodified, might page to disk and do page replacement, and then your hypervisor might also do page replacement as well. And you might want control over this because typically the guest knows how memory is accessed better than the hypervisor. So there's some trade-offs here where you actually want your page replacement done, and it gets much more complicated that we'll kind of ignore for the rest of this. But there's some other concepts we learned that would apply to this. So for example, sharing read-only pages. Well, we do that in processes all the time, but if you want to do that in virtual machines, well, you could still do that. So if you have 10 virtual machines running and they're all using the same kernel, well, ideally, I just want one copy of that in physical memory. But unlike that, there's no like fork for virtual machines or something like that. So similar to that, so we're going to use the same idea, but now to identify pages that can be shared, the hypervisor is going to have to scan through all the pages. And if it had to scan through them byte for byte and see if any are the same between virtual machines, that would be very, very slow. So what they do instead is check all the hashes of the contents of the page. And then if 2 hashes are the same, then it's possible they're the same or possible it is not. So only if the 2 hashes are the same, which is relatively fast, then it will do byte for byte checks to see if the pages are actually the same. And if the pages are actually the same, then it will go ahead and share them. And then it will enable the same optimization as we saw before, called copy on write. So that way, if either virtual machine actually modifies the page, then it would make a copy that has a copy of the page and actually do the modification there. So another thing it can do is virtualize I/O devices. So if you have a network card, one thing you can do is multiplex one device to multiple virtual machines. So you have one network card, but all your virtual machines could use it if you so choose. Other options you have is you could map one physical device to a virtual device in one VM so that that virtual machine has exclusive access to the device, but the hypervisor is still going to be in the middle of it and actually still translate any usages of that device. So there's a new-ish hardware solution for that to remove the hypervisor, and it's called IOMMU. So only newer systems will have this. And that is a way for the hypervisor to directly map the physical hardware to the guest, and that guest actually gets access to the physical hardware and has to manage it itself. So the VM now for sure has exclusive access to the device and has exactly the same access to the device as if you didn't have a hypervisor at all. So this allows something like GPUs to run at native speeds in virtual machines, because if you're running something on a GPU, like some machine learning thing or a game, well, you want all the performance you paid for, so you don't want anything in the middle of it slowing it down. So if you have this, you can run your AI training or whatever at full speed and still get all the benefits of using a virtual machine. So when you actually want to boot a virtual machine, the last thing is a disk. So virtual machines just boot from a virtualized disk. So all you have to do is create a disk image that has all the contents of the physical disk. So it would contain like the partitions, and then each partition would have a file system like FAT that we saw before, or an inode-based one. So usually it's just one big file, but some formats allow you to split it up or do some compression to optimize things a bit. But this file, the guest kernel recognizes that file as just a normal disk and thinks it has full control over it. And then if you want to use a virtual machine, like a normal machine, all I have to give you is a disk image. So that's all you need for a virtual machine. Makes it easy to move around as well. So if we so choose, which might have been better, especially for Lab 5, is we could have just created a disk image for the UG machines and then given it to you and told you to run it as a virtual machine. And then all the hardware would have been the same, except you're guaranteed that no other user is on it fighting for resources, and you actually get slightly more consistent results. So that's all you would need. And then if you download some of these virtual machines, you might see something called an OVA file, but that basically is just a disk image and then some configuration settings for the guest, like saying how much memory should the guest have, how many CPUs should it have, etc. But all you really need for a virtual machine, aside from some configuration, is a disk image, and you can use that virtual machine. And any changes you make while running that virtual machine, well, they just get saved directly to that file. So you could even move that virtual machine to a new computer later, and everything is going to be exactly the same. So that's what I'm using for, all the lectures, all the examples I've shown for like code examples. Well, those have all been in a virtual machine, especially because you guys have like made me like tried to kill init and all their weird things that I wouldn't want to do on my real system. So it's just a virtual machine, and whatever happens to it doesn't really matter. And because it won't bring down my actual hardware, because it's a virtual machine, I can just reboot it without anything bad going on. So this is where we get to the containers and what Docker is. So one idea people had when people started using virtual machines is like, wow, this is great. Everything's so nice and consistent. Updates don't break anything. Everything's completely isolated. So people started like what we had before with dynamic libraries. Well, if you're maintaining a big system and someone hasn't followed this course and writes a very bad dynamic library that completely breaks some applications, well, some applications might update and use the newer version. Some might be old and use the old version. So if you update the version of the library, half your programs work, half them don't, and it's a complete mess. You either need to have multiple copies and fix it up or do something about it. It's just a complete mess. So what you could do is actually create a virtual machine for your application that has the libraries on it that it needs, and you're for sure guaranteed they're the correct version. So everything just works. So your application is just in a virtual machine. Everything's nice and consistent. One update doesn't affect the other one, and everything is good. So you freeze your dependencies, you deploy it in production, and no matter what, it's going to be the same experience. As long as the machine can run virtual machines, it can run your application. So I could give it to you running, if you're running Windows, if you're running Mac, if you're running Linux. Doesn't matter, I give it to you, it works. Simple as that. So the drawback of that is if I have an application and I package it as a virtual machine and I give it to you, well, the virtual machine is going to contain a kernel. So all of your virtual machines for all of your applications are going to contain a kernel, and your kernel is going to be like at least 700 megabytes or something like that, and your application might be like, a handful of kilobytes, in which case I am transferring, almost a gig, so you can run my application when most of it is kernel that isn't actually super relevant to the application, so I'd rather just not transfer you a whole kernel. So that's the idea of containers. So containers, so something like Docker, aim to behave exactly like that, where you can just package up an application real nicely with all of its dependencies and you don't have to worry about anything. But it wants to be faster and actually use the same kernel. So if we go back and we remember, why we actually want to do these things. So in addition with freezing all the dependencies and everything, we also get some nice benefits of the hypervisor where you can set limits on the CPU time, network utilization, memory, things like that. So the Linux kernel supports these hypervisor-like limits just on normal processes. So the Linux kernel actually supports this with something called control groups or C groups, and they allow you to set limits for processes and isolate them to a namespace, even isolate their access to the file system so they can't even see the rest of the file system, limit their network access, how much memory they can use, how much CPU they can use, and all things like that. So Docker uses that, and so Docker uses control groups to run a packaged application without the need for the application to actually give you the whole kernel every single time. So it reuses the same kernel, gets all those benefits, and you don't have to transfer the kernel because it's just going to use the already running Linux kernel. So and Docker is specifically built on top of the Linux kernel. So if you're using Linux and you're using Docker, you're just going to use your kernel. But if you use it on Mac or Windows, well, Docker is going to run the Linux kernel in a virtual machine for you and then run all your applications using that virtual machine. So there'll only be one virtual machine for the Linux kernel if you're not a lucky benefactor of actually running the Linux kernel natively. and then go ahead and run everything on top of that one Linux kernel. So you don't have to distribute a kernel with your application. So the idea of this is they're going to be much lighter weight. They don't need their full kernel. They don't need to have nested page tables or anything like that. They can just go ahead and use, if you're running the Linux kernel, you can just go ahead and run it as a normal process, which is nice and fast. So they just use the normal kernel. So that's it. So virtual machines virtualize a physical machine, so they allow multiple operating systems to share the same hardware. They provide isolation, and a hypervisor is the thing that controls them. So type 2 hypervisors are slower because they run in user mode and they have to emulate or simulate any kernel-only instructions, either using trap and emulate if the ISA is designed correctly, or actually do some binary translation and look to see if it needs to handle it differently. Then type 1 hypervisors actually have hardware support. They have I/O, something like IOMMU is going to speed up access to devices by just giving that virtual machine access to the physical device. And then hypervisors might overcommit on resources and need to physically move a VM, which is able to do with virtual machines. You can move them across servers, and that's why any single cloud provider, they only use virtual machines. And then containers try to have the benefits of virtual machines without the overhead by basically not providing a kernel. So that is it. So just remember, pulling for you, we're all in this